1 minute में.
Now we are going to do the experiments on the Tafel. So in the Tafel, that what users want to know that they have some metal plates and do the coatings. How far this coatings protects the metal surface. So what I need is I need a sorry. See that can you able to see that the surface area? Can you able to focus it? The area that which is that if you can see that inside, could you able to get a focus? So there that is a sampling area. So that even though if I am going to use that big electrode, so only that much area is exposed to the solutions during the measurement. So what I am going to do is I want to insert that what I call the electrode. So simply that I am inserting it. So there is a mooring that which will make sure that the solution does not leak. Now, yeah, it's holding it properly, and I have to ensure that there is no leak. Can you able to see that the electrode surface? Can you be able to focus it? Yeah. Done. Now what I wanted to add is I wanted to prepare that sodium chloride solution. So sodium chloride, I have to add. Sometimes people take 1 molar sodium chloride, some people take 3 molar KCl. Sorry, sodium chloride. Where is the sodium chloride? Can I get some sodium chloride? Raghavji, where is the sodium chloride solutions? Yeah. It is stop for a while. Yeah. Now I have no idea which potential to start with. So I am not proceeding with that the experiment. So I want to get a feedback on the what do you call that? Open circuit potential. Now you know that I am disconnecting the leads from the old experiment. I am removing that my cell holder. I kept it away, and I am taking a corrosion cell. I could see that I prepared a 3 molar sodium chloride, and you can decide that you want to go with the 3 molar sodium chloride or with the 1 molar sodium chloride. So depending on the experiments, and I am placing a counter electrode which has a huge surface area. So platinum wire with the wire gas, which is a spot welder. So this is to increase the surface area which I inserted. And working electrode is my sample. Reference electrode I have to use it. I'm taking a reference electrode, so wiping it off. Fine. And I'm using my reference electrode. I'm throwing my reference electrode. So now I have to give a physical connections. So since my electrode surface is conducting, I can afford to clip that. If it's a small surface, there is a one more clip to connect it. Since it's a larger sample, I can connect from the top. Counter electrode, I am giving to the platinum flag electrode. AGCL, I am connecting to a white clip. So my electrical connections are through. I am ready to do the open circuit potential time. Done. I say 400 seconds. I say OK. I'm running it. So what is the potential? It is somewhere around minus 1.0. So that bare metal comes around that minus 0.4, minus 0.5, and so it's very close to 0. So that's the reason that the air itself sometimes that some of the metal it oxidizes. So the thing is that when the OCP goes down, so that means that coating is reasonably good. The OCP itself tells us that okay, that we are getting the coating is better. So it is minus 1.0 and it is stable. Can you able to see that a flat curve? Sometimes we will see that what you call that it stabilizes over a period of time. So you have to feel that equilibrium time to start the measurement. Now I am ready to start. So minus 1.07 is my potential. I say stop. Now I come to the technique called Tafel. I am choosing the Tafel plot. Okay. Now what is my initial and what is my final? So this will be basis for my initial and final. Any Tafel users will be oxidizing the samples. So always we start from the negative potential, we have to go towards the positive potential. So from the OCP, that is the plus or minus 200 volt is the scan potential. So I start from minus 1.2 and I can go up to the plus 0.8. So that is my initial gas. I say initial is minus 1.2. That means that I am taking most negative potential and I am coming to minus 0.8 volt. So my OCP is 1 volt. So I am scanning from minus 1.2 going up to minus 0.8. So that is that. Now that after this potential, my that surface will get oxidized. And what is the current we expect somewhere around that electric surface is little more. I am not sure since I am going to measure the log current. I am just at 10 power minus 4 auto sensitivity. Scan rate is 10 millivolt per second, but people go still that lower scan rates. Since the experiment will take a long time, I am using that scan rate as such. I say okay. So segment 1 means that it starts from minus 1.2 and it ends at minus 0.2, it stops there. I say okay and run. So I expect that somewhere around that that my peak has to come around somewhere around here. Let me see that. That's my expectation based on my OCP. I'm not seeing anything in the screen. Yeah, now I could get it. So I could able to get that. Somewhere I expected somewhere around minus 1. I'm getting the peak over here. So sometimes at whatever the expected peak, it may not appear on the same potential. See, now this is the corrosion potential, and the surface is getting that whatever the oxidation surface, protecting the surface. This is the potential dynamic deactivation region. Okay, I am getting that. Let me click on that things. So now I am getting it properly. So the thing is that I am getting it somewhere around where I am getting it. I expected minus 1.07. I got around minus 1.12. So the thing is that am I happy with this one? No, I am not happy. Why? Because I am starting very close to that my oxidation peak. So the thing is that what I have to do is I could have started little ahead. So in any Tafel experiments, the only problem is since we oxidize the surface, the electrode that surface get it's not, surface is not same anymore. We have to change the surface. So either I have to push it little bit on the side. I have to take a new surface area. In corrosion, there is something happening at the surface. So we cannot able to use the same surface. So I change the surface little bit. Now I am not happy with the initial potential. I go further to minus 1.3. I say okay. I am running the experiment again. So little bit of improvement I am doing it with the initial potential. My calculation went minus 1.07. Actually I calculated as minus 1.1, but I took as 1.0. So that made a small difference. Now that let me see that I need to get to make a tangent. I need to have the right. I'm not sure again either I can get a right tangent. Now that with this experiment that my software will not automatically make a tangent. I have to make a tangent myself. I have to use a manual keys. So this this is my reduction potential, oxidation potentials, and this is the potential dynamic deactivation region. Fine. So that is fine. It's approximately again that minus 1.07. What I expected has happened. So that was OCP was minus 1.07. I'm getting it. So that is fine. Now I am happy. Okay. Now what next? I'm going to analysis. What is special analysis? I am asking software to calculate the corrosion current, the anodic cathode slope, and linear polarity resistance kind of things. Calculate. Software calculated, and it is given the results. Are you happy with that? No. This what you call that? Basically, it looks at that what you call this potential. You try to do that. Some of that this is not intercepting the things. So that is because of the chemistry behind the layers, which as a user we do not have any control. Yes, user can only do a equilibrium and do the measurements. So the results that coming that exactly that a theoretical curve like this, it's not in our control. Now what best we can able to do is so analysis, special analysis. See, now if I have to see that this tangent seems to be good. This tangent I have a liberty, so that I can choose this as a what you call that my tangent, or I can choose this as what you call tangent. So that my feeling is that if I choose this as a what you call the tangent, if I start here and probably this and this will give me that what you call correct tangent to intercept over here. So what is the potential? Somewhere around minus 1.0, and this is around minus 1.01. Okay, let me check that. So what I do is analysis, special analysis. So there is a which number I may have to change. 1.01 to 1.0. This would be minus 1.0. Let us say that calculate. Okay. Did it do? Minus 1.01. 1.0. Why it is not doing that job? What mistake I am making? Can anybody able to improve that now? Which potential I have to give? Can anybody make suggestion? What is this potential? Minus 1.01.
Minus 1.03. Minus 1.03.
Minus 1.01 and minus 1.03. Simulation, not simulation. Minus 1.03 and minus 1.01. Right? Let me try now. Calculate. Okay. Is it fine? Further improvement is needed. Which one I can go out further? So I can give the body call further this side.
1.005.
So analysis, special analysis. So can you shift that body call that?
1.01 to
04 and
1.005.
02, 1.04 and 02. Let me see that.
It will go up.
I'm slightly going with lighted air. Also the thing is that which is almost acceptable. Now cathodic slope has been calculated by software, anodic slope has been calculated, linear polarization and corrosion current. This corrosion current is the indication that how much that what you call that metal is getting oxidized. Each metal that there will be 2 electrons. So if you remove the 2 electrons and that one oxygen will bind with that oxide forms. So this corrosion current is indicative that how much that oxidation happens. as long as corrosion current is less, you can see that oxidation is prevented by the layers properly. Okay, now I'm happy with the experiment. I'm saying that save as. So this is my Tafel 1. And what is the sample? Anybody has an idea? So I do not know that what is a coating, so I am writing as a Tafel 1. So I have to compare the two coatings, and I have to say that coating 1 and 2, I have to compare it. I am saving this one. And is it possible for me to calculate that corrosion rate in mils per year? So I have to mention the area. It is at 5 r squared, 3.14 into 0.5 centimeter into 0.5 centimeter. So what is the answer for that?
78.
So
0.78.
0.78 is my surface area which is being exposed to that sample. Formula weight of that is it zinc or what? Which metal it is?
Zinc only.
65.
Zinc, that atomic weight, I am assuming it is 65. It's a 2 electron oxide formation is 2 electron oxidations. And what is the density of that zinc? Anybody has an idea?
5.6.
Huh?
5.6.
6.5.
Should we check it? 5.6 again. I have to verify that. I am saying that 5.6 as I calculate. As I okay.
7.1.
7.1 is the zinc. So I am coming to analysis, special analysis. I say that it's a 7.1. Let's calculate. So okay. Now cathodic, anodic slopes, linear polarization, corrosion current, corrosion rate in mils per year, corrosion rate angstroms per minute, corrosion rate in grams per hour, but everything has been calculated by the software and it is given that. Okay, now I'm happy with the experiment so far. So that I saved it also. Now I have to do the what do you call that? I have to do the okay. Now I have to do other sample. Okay. Can you pause it? Yeah, I can replace that another coating on a zinc. Now that I'm ensuring that there is no leakage, I'm replacing that rate. So I kept that cell back. I have to give the electrical connections. Working electrode has been clipped. Counter electrode and the reference electrode. Connections are through. Now the experiment is to be done. So again I need to do a OCP technique. Open circuit potential. Say OK. 400 seconds. Run. And I'm checking that if there is any change in that potential, if there is any change in the equilibrium. It shows that somewhere around minus 0.97. The previous one was at minus 1.08. The experiment seems to be that coating of the previous one is better. So for that, yeah, now the thing is that I could see that what do you call that, the peak, I could see that it's around minus 0.98, something like that. And I think that you see that this sample is not that what you call that, not stable. The equilibrium is not achieved. So now I could see that relatively that stable numbers. The thing is that I mean, I expect normally that the changes in the last digit. That here the changes are happening in the second and sometimes on the third digit. So that means that the equilibrium is not established yet. Sometimes we may have to look for that what you call that air bubbles kind of things. If the air bubble also that, then it will be the absolute what you call that. Just I am disturbing physically. So I am seeing this the air bubbles will get rid of it. Fine. So it was minus 0.98 and now it came to minus 0.96. What is worrying me is that what you call that stability. So I need to have a flat what you call that OCP. So then I can say clearly that the equilibrium has been established. Sometimes cleaning the surface also sometimes helps. So I am ensuring that no air bubbles, surface duct or the surface contamination also that affects that experiments. I could have cleaned it that while putting that electrode back. So that while cleaning, before putting the sample, I could have cleaned it a little bit. So that eliminates that one possibility. You will end up in having that only problem of the equilibrium. So minus 0.95, something like that. So I'm not happy with the things so far. So what I do is, I will stop now and I will clean the surface and put it back. Let's see what happens. So as of now that I'm not happy with the what you call the OCP results. So I need to have stable OCP. I'm stopping now. So what I do is, I want to clean that the sample further. So I'm first disconnecting all the electrical connections. Yeah, anybody can help me in cleaning the surface? Clean the surface and give it back. Change the surface. Now I'm done the electrical connections. Starting the experiments again. I want to make sure that there is no noise in the measurements. There is no noise seen at what I call that so far. The oxidation process is going fine. Coming back, some click, after that the noise starts. So that I could see a click from the instrument, some relay changes. After that the noise starts. There is another relay sound. Now I do not know what to do that. So at this point I stop the measurement and I want to make sure that my hardware is correct. I do a hardware test. Hardware test seems to be fine. So and I assume that what I assume now that again now let me ignore that what you call that the noise. Really I do not continue the noise as such, but still that I am trying to continue that. I go for a special analysis. I say calculate. I say okay. Now it's not doing the job. Software is taking arbitrarily, so I have to take between the minus 1.1 to 1.05. So I say that special analysis. Minus 1.1 to 1.05. And this one I say that what I can take that between that. Can I take between that minus 0.94 and minus 0.95 and minus 0.97. I can try now. Yeah, I'm stuck. Now, right now that what is happening that I cannot do the stress analysis. First I will say this one is Tafel to say I do not like the noise in the measurements. Still I go with for the overlay and plots. You see that. So out of the two samples, this sample seems to be that what you call that much better. So all that the bare metals, it's very close to the 0 volt. So that is the reason that it get oxidized in the air, like wrought iron or that most of the metals it forms the oxide layers because the reduction or oxidation potential is very close to 0 volt. So we basically that we are doing some coating to improve that what you call the coating efficiency. So compared to this coating is far better. So that is the results we got out of it. And in this sample that we could able to do that what you call that Tafel current calculations. So here that somehow that's a noise in the measurements. Because of it I cannot able to calculate the corrosion current, the linear potential system and percentage I cannot calculate. But the experiment tells me that the out of these two samples, the Tafel one sample is the coating is a good one.